السلام عليكم.
وعليكم السلام.
هل في أي أسئلة من المرة اللي فاتت؟
تمام واضح.
طيب واحنا النهارده ان شاء الله باذن الله هننتهي من we're gonna finish basically the rest of the theoretical part of the course, and basically on Sunday inshallah I will give you an outline of the topics that will be included in the exam. Okay, so on Sunday we're going to go over each one of the topics that we are going to include in the final exam. Okay, have you had any chance to agree on a date for the lab exam and the project exam? We need 15 minutes for each. 15 minutes, just maximum of 15 minutes. 1-5, okay? Have you agreed on a date and time for it?
Doctor, I think some people agreed on like 7th of April and other people agreed on the 11th. 7th is the last.
Which one is which? But we need both. We need two dates. One for the lab exam and the second one for the project. So basically the first one should be for the lab, okay? I think the 7th would be great because actually the lab exam is really easy. Basically, it's just the basics, okay? So basically it shouldn't be a problem for any of you actually. You just read the experiments and basically remember you know, of course, you know the tools that you used in the lab, like the function generator, the power supply, what they do, and the oscilloscope, of course. So a multimeter, things of that sort. As long as you actually did the experiments yourself, you're not going to have any problem solving all the questions correctly. Okay. So basically, it shouldn't be a problem. You don't really need the preparation for the lab exam. Okay. So if you don't mind, if you all don't mind, maybe you can include it on the 7th, okay? If it's okay with all of you. Does anyone have an objection, you know, on the 7th? If you have the lab exam on the 7th, April 7th.
Doctor, I just have a question. So if the lab exam is on this, have you specified the project exam or not yet?
No, I'm just talking about the lab exam for now. For the project exam, basically, it should be after the date when you actually after the due date for the project. So whenever you agree, it shouldn't be more than 15 minutes. Also, it should be straightforward. As long as you did the project yourself, you participated in the project basically with your colleagues, you're not going to have any problems because you're going to have your report with you in the exam basically. I'm going to be asking you about things that you already wrote in the report. That's it. So basically these two exams, first of all, they are going to take only 15 minutes each, 1-5, not 50, 15, okay? 15 يعني, okay? So basically, they are not going to be that big of a problem. They are not going to take much of your time. They don't really need much preparation. As long as you did the experiments yourself in the lab, you should be able to do the lab exam without any problems. As long as you participated in the project report, you shouldn't have any problem solving the problems in the project exam. So I don't see any problems actually. If you want to combine both of them in like consecutive exams, like having one and then the next in 30 minutes, it's fine with me. Okay. If you don't mind, let's settle the lab exam first. Okay. If you don't mind, do you mind? Does anybody have an objection on the date of April 7th for the lab exam? Do you have any issues with the lab exam on the 7th?
No.
Yeah. Okay, so basically I'm going to send an announcement for the lab exam, and hopefully by next Sunday, you agree on another date for the project exam. Okay. Also regarding the final exam, do you have an opinion about which date would be suitable for most of you at least?
Can we take the final exam after the 16th of April, or
you can do that? But actually, it's preferable to be before that, so that you don't have any conflict with other exams. it's fine with me. If you agree on a date after the 16th, it would be fine. But basically consider this. We're gonna be done with the course today. Next week, we're gonna be reviewing basically the different parts of the course. And basically after next week, you should be ready to take the exam anytime. So it would be actually a good thing for you to get it out of the way so that you can focus on the other courses. So it's up to you. I'm telling you that it might be better to have it earlier. But if you want to have it later, that's fine. If you agree on another date that is later, I'm going to be fine with it. Okay? So if you have it settled on
because I have...
yes.
Sorry, I was going to say I have few finals on the same week, so I don't want to like have pressure on that week.
That's fine. So basically, try to agree on a at least most of you would agree on particular date and let me know of it. Okay. For now, I'm going to be sending an announcement about the lab exam for now. Okay.
Okay.
Okay. So let's go back to the last part of the sensors topic of the course. Basically, we talked last time about the piezoelectric effect. And basically, the piezoelectric effect includes the fact that basically, if you have a piezoelectric material like this, if you apply pressure on that material, you're going to have basically a positive voltage on one side and a negative voltage on the other. If you actually pull it apart, so basically, if you basically pull it on the other side, pull it toward the outside, you're going to have the opposite charge on the same material. So basically, you can convert pressure into voltage, okay? And this is basically used to be able to receive or at least measure pressure or basically measure pressure waveforms. So you can use something like this actually to basically as mics. If you have the microphone that you use, usually it's made up of piezoelectric material now, okay? This is the most common technology that is used at this time because it's actually very convenient. It's very small and it's really very sensitive and actually can be used quite reliably actually in this application. We talked about several applications. Basically, the most common one that you probably saw is basically the parking sensors in the cars, which look like this. Basically the element here is a piezoelectric material. And basically what you do here is just send the waveform, send the pulse of ultrasonic wave. This pulse is basically like a pressure, like a voltage waveform. So basically the piezoelectric material converts voltage to pressure and pressure to voltage. So basically it works reversibly between the two, okay? It can work from voltage to pressure, or if you have pressure, it will convert it to voltage. So in this case, what you do is basically apply a voltage waveform so that you can create a pressure wave. And this pressure wave goes outside, sorry. Okay. Goes outside, okay, basically, and basically when it hits an obstacle, basically it goes back. And basically, you know exactly how much time it would take actually to go back and forth because you know the velocity or the speed of sound in air, which is about 340 meters per second. So basically, when you have the reflected wave coming back in like a few milliseconds, you can actually compute exactly where the obstacle was. And this helps people know exactly how far the obstacle is and basically use that to guide parking, for example, in this application. There are some very simple transducers that are used for Arduino, for example. These are used actually to measure distance. And it's based on two piezoelectric transducers. But in this case, it's not just one like this. In this parking sensor, you send and receive with the same transducer. Here, you have one to send and another one to receive. Based on the distance between, or that basically when you send this, you wait for the signal to come in this and measure the time between the two and determine the distance based on the time difference between the two. Okay, but in this case, you actually use two different transducers, one for sending and one for receiving. Okay, sometimes it's easier, it's much less complicated in the circuit point of view to have a different sensor for sending and receiving. And basically, if you look at ultrasound imaging that is used in many medical applications, all the ultrasonic transducers are made up of piezoelectric materials. And what we talked about last time regarding the piezoelectric materials is that they are very sensitive to temperature. If you raise the temperature beyond a certain level, they will lose their piezoelectricity. Meaning that if you want to, for example, sterilize one of these transducers, common sterilizers use heat and steam, high pressure steam, basically to sterilize. If you use such techniques on ultrasonic transducers, they will not be ultrasonic transducers, basically. So basically, they are going to be clean, but they are not going to be ultrasonic transducers. You're not going to be able to use them any longer, okay? And these are really expensive. So basically, you're not supposed to expose piezoelectric materials to heat in order for them to keep functioning as piezoelectric materials, okay? Do you have any questions about piezoelectric materials or piezoelectric effect? Okay. Another very interesting sensing technology is what's called the Hall effect sensors, okay? So in the Hall effect sensor, basically, if you have a current passing through the Hall effect sensor in this way, and there is a magnetic field vertical or perpendicular to the current in this way, there will be a voltage basically in this way. There will be a voltage generated in this way depending on the amount of magnetic field that is there, okay? So basically this is because of a very simple phenomena. When you have an electric current, it's made up of electrons. If you have a magnetic field, there will be a force on the current. Basically, if you remember that there is a force, this is exactly the same force that we talked about in the moving coil. You have a current passing through a conductor and you have a magnetic field, there will be a force that is proportional to the magnetic field and the current. So basically, in this case, the current is flowing here and the force will be actually applied on the electrons themselves. So what's going to happen is that the electrons will be actually, they tend to be in one side or basically tend to be moved towards one side over the other. And this actually creates a certain, basically preference of charges from one side to the other. And this preference of charges will actually create a voltage. And this voltage will be proportional to the current and the magnetic field. So this can be used very simply in, for example, if you know if you want to know if the door is closed or not, for example, okay? What you can do is have a part like this that is made up of a magnet, and this is a piezoelectric, this is a Hall effect transducer. When these come close to each other, there will be enough voltage to basically sense that these are close enough and basically sense that the door is closed. If they become apart, then the magnetic field will become very small or non-existent. This means that basically you're not going to have any voltage and you will be able to sense that they are not in proximity to each other, okay? So basically these can be used to sense proximity. Proximity means that two things are close together. Another example, basically in refrigerator doors, okay? They used to have a micro switch, so that actually when you close the door of the refrigerator, basically the micro switch is pressed, so basically the light turns off and basically you know that the refrigerator is off, it's basically closed. Now we use Hall effect sensors. They don't have to have a mechanical switch. They just put in the door itself. They put on one side, they put the Hall effect sensor. On the other side, they put a magnet. And basically when they come together, they can actually detect that there is a voltage coming from the Hall effect sensor that actually indicates that the door is closed, okay? Hall effect sensors can be very small like this. So basically they can be something like this. Usually they have 3 pins. Basically you put one of them, you put as ground and the other one you put as a voltage, sometimes it's around 5 volts, okay? And basically on the third pin, between the third and the second, you detect the voltage. So you get an analog voltage, and this analog voltage will be proportional to the magnetic field and the current. Since the current is basically constant, because basically you have a constant voltage here, so basically what you're going to get here is proportional to the magnetic field. So it will indicate the proximity of the magnet from the Hall effect sensor. And you can use that in many applications. Okay? Any questions? Okay. Let's start talking now about the temperature sensors. There are so many different technologies in temperature sensors, but we're going to focus on 4 different technologies that are most commonly used. The first one is what's called thermoresistive effect, which means that temperature creates resistance or modifies resistance. Okay, so basically in this type of sensors, basically the resistance will change depending on the temperature somehow. Okay, in the first type, the linear type, which is called RTD, resistance temperature detector, we saw that if you have a particular resistance at a particular time, a particular temperature, basically you're going to have the resistance will have a temperature dependence that looks like this. This is exactly the same equation we saw in the resistance. The temperature, this is the temperature coefficient of resistance, okay? And basically, and this is the delta T relative to the temperature where the alpha is. So if this is alpha 0, for example, this will be just simply T. If this is alpha 20, then this will be actually T minus 20. So you saw that before. And in this case, you only have to have a resistance. So basically, this sensor is just a resistance, just a wire wound resistance. And basically, you can detect the variations in the resistance. And basically, from the variations in the resistance, you can compute the variations in the temperature accordingly. Okay, we already did that. You saw some problems when we talked about a motor. When it starts at temperature 20, for example, or 17, one of the homework problems was like that. The temperature at 17 gave a resistance of something, and then when it worked for about an hour, the temperature became a little bit higher, and the resistance became a little bit more. So basically, from the amount of resistance, the new resistance after the temperature increased, you can actually detect or compute the estimate of the temperature based on this equation. There is another type that is nonlinear. We also talked about in the resistance, which one of the examples is the NTC thermistor, negative temperature coefficient thermistor. Okay, this is the most commonly used type. There is another type that is positive temperature coefficient thermistor, which looks like this. For the NTC, the resistance of the NTC thermistor changes with temperature this way. So this means that when the temperature increases, basically the resistance of the NTC thermistor decreases, not increase. Basically, if you're talking about the RTD will be just like this, okay? So basically, to be basically linear. But actually, for the NTC, it's going to be low, basically going lower like this, okay? For the PTC, actually, it has a curve that looks like this, but this is really very steep, first of all, in this part. And basically, this is the positive slope part. And usually, it's not very, you cannot really use it in the range for human temperature measurement, for example, because actually, it starts after 100 degrees centigrade. So if you want to measure temperature in the regular range, like from 0 to 100 degrees centigrade, so NTC thermistor would be actually a very good choice. There is a curve for it. You can actually have an expression for it, but usually you don't do that. You usually have certain characteristics that are given in the data sheet, and basically use that characteristics to be able to determine the temperature based on the resistance that you measure. So basically, you can have something like a table or like a different equation from this, or a similar equation to this with a constant. This was given as a particular value, so that it allows you, given a temperature, given a particular resistance of the NTC thermistor, you can actually detect exactly what the temperature is. Okay, so basically here you cannot compute it as simple as this one here. It's not a linear curve. It's a much more difficult or much more non-linear curve. So basically you need some equation or some sort of a table so that you can actually convert the resistance into the temperature. Okay. Usually what you see in Arduino temperature sensors that are based on thermistors, they are more like temperature IC types. And we're going to talk about them in a short while. Okay, so basically they will have the thermistor, and they will have actually some digital circuits around it so that they can actually communicate with you directly the temperature. You don't really have to get a resistance and then convert the resistance to voltage and then convert the voltage to digital form. Now, actually, for usually for the commonly used sensors, they have a digital interface where you can basically communicate the temperature directly with the microcontroller or whatever. But basically, in concept, they are these two types of sensors. They are based on thermoresistive effect, which means that temperature variations change electrical resistivity of a particular resistance. Okay. You have any questions about this? Okay. There is another effect that is called thermoelectric effect. There is a difference between thermoresistive and thermoelectric. Thermoresistive means that you have temperature variations causing changes in resistance. Here, temperature variations will be causing an electric change. Okay. Here, actually, we're talking about a voltage. Okay. And this is actually one good example of this. Actually, is the thermocouple. And basically, what sometimes they call it thermoelement, but usually thermocouple is a much more common name. It's a junction between two conducting materials, and usually two metals. Okay. And basically, this is type A and this is type B. And they have a junction here somewhere, basically between the two. And basically, you measure the voltage between the other two terminals of these two conductors. Okay, so whenever the temperature changes here, you're going to get a voltage here that is proportional to that temperature variation on this side. Okay, but actually, this is basically, it generates a voltage. So basically, it's a passive sensor, meaning that it doesn't need electricity. The ones before that we saw, the thermoresistive ones, since they actually convert the temperature into resistance variations, you will need power supply to convert the resistance into current or voltage variations. So basically, the thermoresistive were active sensors. So basically, this is an example of a passive sensor. There is another issue here for this particular sensor is that basically, it depends on the output voltage actually is a constant times T2 minus T1. T2 is basically the temperature at this junction, okay? And T1 basically, maybe this is opposite of this actually. Basically, it's here supposed to be T2 and it's supposed to be T1, okay? So basically, it's a temperature difference between this point and the point of measurement on the other side here, okay? So basically, what you're gonna get is a relative measurement, not an absolute measurement. So the voltage will not be, you're not going to be able to measure the voltage directly, but you can actually measure the temperature relative to a particular other temperature, a reference temperature. Okay. Somebody can say that basically we're trying to measure temperature, and basically, if you want to measure this temperature, we have to measure another reference temperature here. Okay. So basically, we need another temperature sensor, not going to be basically using another thermocouple. So basically, you have to have another temperature sensor at this point here. The thing is, this type of sensors can be used at extremely high temperatures. So basically, this point here can be in thousands of degrees centigrade or degrees Kelvin, okay? And this point here will be usually at room temperature, okay? Or at a particular reference temperature that is much less. Okay, so you can use a thermocouple, you can use a thermistor, or you can use RTD to measure the temperature here. And basically, this will be in a furnace, for example, if you have a sterilizer that has very high temperatures, things of that sort. And basically, this other side will be in the lab or in the measurement department or something like that. And basically, given the voltage here and given the temperature measured here in the measurement lab, you can actually determine how much temperature is at the junction. Okay, so basically this particular sensor has very unique characteristics, which is first that it's a passive sensor, it's a relative sensor, it requires the measurement of temperature at a reference point in addition to basically the point where you actually want to measure it. Okay, such sensors actually look something like this. These are actually examples of practical thermocouples. So basically here you will have the junction somewhere here, and basically this will be a very long wire so that you can actually take it to, a long distance, away from the furnace or the very high temperature that you're trying to measure. And basically you have the reference temperature between these two actually as the reference temperature for your measurement. Okay, and you measure the voltage between these two terminals and basically use this equation. Usually you get the constant here from the data sheet, and you get the temperature, the other reference temperature measurement from another sensor, and you can actually compute T2 based on the measurement of voltage. Okay, there is an expression for the EMF that is generated from temperature. Sometimes they call it Seebeck EMF. Okay, but actually you don't really need to remember that. It's just a thermoelectric effect. Okay, thermoelectric effect means that you're gonna convert temperature variations into electric variation, like a voltage. Okay, have any questions? The last type, which is the most common type that you are likely to use, basically, for example, if you work with Arduino, if you look at temperature sensors for Arduino, most likely you will get a sensor that is based on semiconductor temperature dependent, temperature sensor. Basically, it's usually, sometimes it's just a thermistor, because actually thermistors are made up of semiconductors, but sometimes it's just a semiconductor diode. Okay, and usually you have a calibrated voltage versus current characteristics depending on the temperature, and basically based on that, based on your measurement inside the IC, you can actually determine the temperature. But sometimes it can be, as I told you, it can be just a thermistor, and you have the conditioning circuit that converts resistance into voltage, in addition to a digital circuit that takes this voltage and converts it into an analog, a digital value, and basically communicates it with the Arduino, for example. So you might find a temperature sensor that you can communicate with, like serial communication, for example. Use a serial communication port in Arduino and basically get directly the measurement from that sensor. Okay, and basically in this case you will find some temperature sensors with different quantization, meaning that their accuracy will be different. Sometimes you get the temperature measurement in steps of 0.5 degrees or 1 degree even. Sometimes you get it in steps of 0.1 degrees. Okay, so basically it might be a good idea to actually basically consider several temperature sensors in order for you to get the temperature sensor with the quantization and the accuracy that you want. Okay. So basically, sometimes you can actually get the output in analog form, but actually for most temperature sensors, you actually get the output in digital form. So basically, analog form, output in analog form, it can be actually, you can find some ICs with an analog output, but usually you get a digital form because actually it's much easier to communicate with. It's much easier if you want to put it in a circuit. You don't have to put an analog digital converter. You don't have to use an analog digital converter from your Arduino or from other microcontroller. So basically it gives you directly the measurement that you want in a digital form. Okay, but that you can actually, it's very common to find analog types if you want to have it in a particular application where actually it just has the thermistor and a very simple circuit inside that converts the resistance into a voltage that you can measure. Okay, so basically these are very common, and basically if you want to do an application using a temperature sensor, I would advise that you use a semiconductor temperature sensor rather than any one of the other three types, unless you have a problem with the range, for example. Okay, here the range is between -55 to 150. This is a common range of integrated circuits. You can work in this range without any problems. But if you need a temperature sensor that can measure 500 degrees, can measure 1,000 degrees, then this will not be suitable. Okay. Another advantage of this type is that basically you can use it directly without any external circuits. You can actually have very small integrated circuits that you can put in your devices without having to worry about the space. This is basically a comparison of the 4 types of sensors. We don't have to actually consider that much. It's just an interesting comparison because actually it shows the different parameters that we talked about, and it shows you how to compare different sensors. So we talked about things like the range. So here we talked about the range before. The ranges will be really very, very different. Here it's from minus 200 to 500. Here from minus 40 to 260. Here from minus 270 to 1750. Actually, it can be higher than that even, okay? For the IC, it's basically much more limited, okay? At least more limited than any of the other ones. The sensitivity here is 2 millivolts per degree centigrade. Here it's 40 millivolts per degree centigrade, meaning that this is much more sensitive. Here it's 0.05. This is actually, it might seem that it's not that sensitive, but actually consider that you're measuring temperatures in thousands of degrees, okay? So here actually you have 100, here you have 1,000. So basically, if you have 1,000 degrees, so basically you don't really worry that much about single degree centigrade when you're trying to melt iron, for example. So basically if you're trying to measure a temperature of 3,000 degrees, if it's 3,100, it's not really that big of a problem, okay? So basically this actually can be suitable because actually the main advantage is the range, basically, and you're talking about very high temperatures, so you're not worried that much about the sensitivity here. For the temperature IC, you see much smaller values, okay? But actually, you don't really have to worry about this because what they usually do is they internally convert these into digital numbers. So you don't have to worry about the sensitivity here that much. So basically they can use the microamperes here to generate enough voltage so that they convert it to temperature with relatively good accuracy, okay? For the accuracy here, actually sometimes the accuracy it's not common, you know, for the whole range basically. So basically you're talking about plus minus 0.5 when it's between minus 45 to 100. It's basically plus minus 1.5 when it's 100 to 500. It's basically plus minus 3 degrees when it's 500 to 1200, okay? Here it's almost the same basically, but actually it degrades, meaning that it becomes higher. It becomes higher than plus minus 0.5 when basically you are over 100 degrees centigrade. Here you can actually see that it's actually like plus minus 4, for example. If you're talking about degrees above 1,000, it can be actually very good over there. Temperature ICs are like plus minus 2. Actually, from what I saw recently, I think this comparison is a little bit old. So it might be a little bit like 10 years, 10, 15 years old. So the current sensors actually have accuracies that are much better than that. So it's very common to find temperature sensors, temperature ICs that have accuracy of plus minus 0.5 degrees centigrade. It's very common. You can actually have less than that even, okay, 0.1 for example, okay? So basically, as a comparison, basically you can see that they are not very different. So what's important once you determine the technology, once you determine that you wanted to use, for example, temperature IC, just look for alternatives and you will find basically accuracies that are much better than this. For the linearity, sometimes it makes it easier for you to process the data to convert basically the measurements into temperature, okay? So for the RTD, it's really very straightforward. It's basically an ideal straight line, okay? For the other types, for the thermistor, for the thermocouple, they might not be as linear. So basically, you might need to have a lookup table or an equation or something like that to convert the nonlinear relationship between the temperature and the voltage or whatever you're measuring, okay, or the resistance in case of thermistor, in order for you to be able to do the measurement. And basically, this can complicate things a little bit. So it can, sometimes if you want to do it yourself in an IC or in a microcontroller, you might need to have some code there to be able to do that, okay? For the RTD, you really need a minimum code to use it, okay? But again, for the temperature IC, since all the processing is done inside, and you get the temperature directly in a digital form, you really don't really need to worry about it. So basically, you just read the temperature value, and that's it. Okay. So the easiest to interface to a microcontroller would be the temperature IC. Remember the response time. Response time basically is the time required for if you have a variation in temperature, for example, how would the resistance change, or how fast the resistance will change corresponding to that change in the temperature. If you remember the response time, it was the time between 10% and 90% of the response. For the RTDs, it's between 2 and 5 seconds. It's very similar to the thermocouple. Here for the thermistor, it's between 1 and 2 seconds. Okay, so basically, but actually, again, you might find things that are much faster now. The response time, the faster the response time, the better the sensor, because it can follow the changes in the temperature very quickly. If you have very, very fast variations in the temperature, it can actually follow it very quickly. Stability, which was related to basically the drifts, basically the drift in the sensor. Actually, they are usually for the resistance types, they are usually okay. Okay, for the temperature IC, because actually they have some processes in order for them to maintain the quality of the sensor composition. So basically, it can be excellent here. So you don't have to worry about it for a long time. The thermocouple, because you have two metals joined together, sometimes there is mechanical tear in that joint. And basically this, after a while, can cause variations in the output. For basically, we don't have to worry about the base value. We don't really have to worry about these. For the drift, the sensor drift, basically, you're talking about variations. Basically, if you talk about platinum RTD, for example, platinum is, of course, there are different types of RTD, but the platinum is probably the best. As you see here, the drift is really very small, 0.01% for 5 years, okay? Meaning that after 5 years, it's just gonna be changing either plus, maximum of plus 0.0% or minus 0.01%. For the thermistor, it's still okay because actually it's, yeah, it's kind of 0.2 degrees to 0.5 degrees per year. Here you have actually much larger changes. Here it's actually 0.1 degrees centigrade per month. This is actually not I don't think this is correct for the present technologies in ICs. So basically here it should be actually as good as any one of these. So usually this is much more stable actually. For the cost, actually, the costs also have gone down. So usually, basically, you can get a temperature IC sensor for maybe 10 reals, 15 reals, something like that, which is like $4, maybe $3, something like that. Maybe it can be less also. If you get it in volumes, it can be much cheaper. Usually, when you buy a component, when you buy only one, you pay a lot of money. If you buy 1 million, you basically maybe the price will be reduced by a factor of maybe 50, something like that. Okay, so basically you can get the components at much cheaper prices when you are considering mass production. Okay, so this is the advantage that China, for example, has. It doesn't produce 100 units; it produces 100 million units. So basically, the mass production is basically what's driving the cost down, so that basically they can compete much better than anybody else because of the volume. So basically the point from this comparison is to be able to see exactly how to compare different types of sensors, okay? So what you would usually do is basically list the parameters that we talked about before, like the sensitivity, like the offset, like the accuracy, like the precision, things of that sort, and basically look these up in the sensor data sheet that you have and decide based on the comparison which one you should use. Sometimes you decide based on the accuracy, sometimes you decide based on the cost, sometimes you decide based on the output type, if it's digital or analog, on the size of the circuit that would be required to use for this particular sensor, maybe for the sensor itself, if it's large or small. So basically you have to actually put a list of specifications and try to basically look up these specifications from the data sheets, and then do the comparison and decide which one would be better for you. What I'm going to do to show you how to do this is probably I'm going to add to the resources a few examples of data sheets for sensors, so that you can actually look at them and basically see how you can actually see whether you can read the data sheet, for example, first, and then how you compare the different sensors together to get basically to make a decision on which one would be most suitable for your application. Okay.
Okay.
There's a different type of sensor that you might not have heard of before, what's called chemoelectric transducers. Chemoelectric means that it converts chemical quantity into an electrical quantity, okay? Examples of such transducers, let me basically explain this sensor here for you. This type of sensor is used to measure what's called transcutaneous CO2. Transcutaneous means that it's you're measuring the carbon dioxide coming from the skin. Basically, you have carbon dioxide inside the blood, and you have basically a part of the tissues of the human being is the skin itself, the skin basically. So basically, the content of CO2 inside the blood will basically balance with that in the skin, so that you have almost basically these two concentrations will be related to each other. One important property of the skin is that it's porous. It has some holes. Okay, this means that sometimes CO2 comes out of these pores in the skin. So you can measure these actually and get an estimate of the CO2 concentration in the human being. Okay, so in order for you to do that, basically you put a sensor like this on the skin. So basically this is the skin. CO2 comes from the skin, comes out from the skin. You have here what's called the CO2 permeable membrane. So this is a membrane that is that has pores, that has holes inside of it, and these holes are big enough to pass CO2. So CO2 can pass freely through this membrane. Okay, and basically when you go here, this actually you have water here, and this water, when it combines with CO2, it gives you carbonic acid. Okay. The carbonic acid will make the pH, basically the acidity of the solution here will be higher. Okay, if you put a pH sensor, there's a pH electrode that can actually be used. A pH electrode can actually convert the level of acidity here into a voltage here. Okay, if you have a reference electrode, you can actually get a voltage output of this. There are different types of this, and sometimes they call it fuel cell or half fuel cell or whatever. Sometimes they call it different things, but they usually involve a chemical reaction, and they usually involve the measurement of a chemical quantity. Chemical quantity is like concentration. Concentration of CO2 in the human being or the human body is a chemical quantity. So here you convert a chemical quantity through a sensor like this into a voltage. Sometimes you can actually get it to what's called a potentiometric sensor. This potentiometric sensor actually converts the concentration of CO2 to a cell potential. To basically, they call this a cell, okay? So basically, they convert it into voltage. Amperometric sensors convert it to currents. Conductometric sensors are actually convert, basically the concentration of CO2 will basically convert the concentration into admittance or resistance, basically. Okay, that you can use another circuit to measure. Okay, in all these sensors, you took a chemical quantity like concentration, you converted that to an electrical quantity like a voltage, current, or resistance. Okay, and so that you can measure that. Okay, do you have any questions? This can be used actually to measure measure CO2 coming out of the skin, or you can actually measure it in the exhaled air, the air that we breathe, basically. So basically, you can use it in different types. You can use it in different applications. Sometimes, actually, if you work with Arduino or try to work with Arduino, there are several sensors in Arduino that are basically measuring CO2. Some of them are actually chemical sensors. Okay, so basically they do something that is similar to that. Okay, to chemoelectric transducer, they involve the measurement of a chemical quantity like concentration of a particular gas like CO2, like O2, like whatever. Okay, and they convert that to a voltage or a current or a resistance so that you can measure. The last type we're going to talk about is the photoelectric effect. You probably heard about that before when we talked about the resistance. Basically, from the name, we're converting light into electricity, basically. There are several technologies that allow you to change or convert the incident light intensity into an electrical quantity. One of them is basically what's called the photodiode. The photodiode looks like this. Basically, it has two leads only. Whenever you have light, this particular diode will conduct basically, okay? And basically you can measure a certain voltage, or basically depending on the amount of light, you can actually determine how much current will be flowing here. So basically, the more the light, the more the current here, okay? You can measure the current coming from here, and basically based on that, you know exactly, you can estimate the light intensity, okay? There's a small variation of this in what's called a phototransistor. Phototransistor has three leads, one for this, and actually there is an external one for this, but sometimes you use it and sometimes you don't use it. If you don't use it, it's going to be very similar to this. So basically, whenever you have light coming in here, this particular transistor will conduct, meaning that there will be a current passing through here. So in these two, actually, what you're doing is converting light into current. So you use a current amplifier or a current to voltage converter. This is a very simple circuit that you can build with an op amp to convert this current into a voltage that you can basically use to do whatever you want. Sometimes these components can be used as linear components or as switches, meaning that for a linear component, it means that the higher the light intensity, the higher the current. And basically, they are like analog quantities. You have a curve between the light intensity and the current. For the switch type, they basically either conduct or not conduct. So basically, these will work as switches, basically. Sometimes if it's just a binary device. So in this case, you can use it to basically, if you want to have something happen when the light comes in or something like that, you basically use this as a switch. So basically, it turns on whenever light is basically imposed or is basically falls on the sensor itself. The third type is based on the photoresistors, which is exactly what we saw before in the resistance. Basically, whenever you have a light falling on this particular type, basically the resistance will become smaller. As we said before, this is made up of a semiconductor device. The light coming in will basically give more energy to the electrons in the semiconductor device atoms, and basically they increase the number of free electrons to conduct electricity, so the resistance will become down, will go down, okay? You can use it as a linear device or a non-linear device like a switch, okay? So basically, you can decide if the resistance is below a certain limit, then it's on, and basically if it's above that, then it's off, okay? So it depends on how you want to work with, okay? There are so many applications actually that you can use for such devices. For example, if you have a belt like this in a factory, you can actually count the number of products coming out by just having a light source here, like a LED or something like that, and here you have a photodiode, and basically you count the number based on the lights on and off. Basically, when you have a light here, when you have this in front of the light, so basically you have no light here, and when it's somewhere else, you basically, if it's in the space between the two, you will have light coming in here. So basically, you get a different signal here. You get a current when this is between the products, and you get zero current when you have the product in the middle between the source and the detector. So basically, you count the peaks, you count the ons and offs, And basically, depending on that, you can get actually the count of the products that are coming out. Sometimes you use something like this to count the people going in a mall, for example. You can actually put this in a doorway and basically know how many people went in, okay? So basically, this can be important also. A very important application is what's called the pulse oximetry. You have a sensor that looks like this. They actually use it very often in the hospitals if they want to count the ECG, if you want to count the heart rate, okay? The heart rate changes with whenever you have basically whenever you have a heart cycle. Basically, at the beginning of the cycle, the oxygen in the blood will be high, and basically at the end of the cycle, the oxygen will be low, because actually it sends the oxygen to all the tissues in the body, and basically collects CO2 and comes back with it and start another cycle. So basically, if you have a light source up here and the detector down there, basically you will receive variations. If you have this light on and get the detected signal, it would look like an AC signal that looks like this, depending on the heart cycle. So basically, if you count the number of peaks here, you can actually know the heart cycle. You can know how many beats per minute or something like that you can actually report for the patient. So they can actually use this to monitor a patient in the intensive care unit, or if he has a certain condition or something like that, just to make sure that his heart rate is okay. So they can use a very simple device that looks like this. So basically, it's non-invasive. It doesn't require any, basically, you don't have to go inside or puncture any part of the skin or anything like that. You just put the finger between the clip device, and just it measures everything, measures the heart rate without any problems. Okay, so that's it for the sensors part. This is all we're going to cover this term. And basically, the plan is from now till the end of the term. Basically, on Sunday, inshallah, I will explain to you the contents of the exam and the contents of the final exam and its style. I'll let you know exactly how it's going to be like. And basically, I have several other lectures. Basically are recorded lectures that I would like to add to the course, but actually I'm not going to include in the exam. So basically, we're not going to have further lectures, but actually I'm going to basically post them for you to look at. One of them is about the power supply unit. One of them is about what's called analog multiplexing. They are kind of topics like this that are really useful if you want to design a project or something like that. You'll need some of these things when you are actually work in an electronic project, or after you graduate, or want to work with power problems. Basically, most of the electronic devices anywhere, actually, the leading cause of malfunction is power supply problems. So if you don't understand the theory of power supply, you will have a problem, basically. Okay, so basically, the plan is to put these for you to go over yourself. And if you have any question, I'll be happy to answer them. Next Sunday, inshallah, I'm going to have, as I told you, I'm just going to review the exam, exam topics, and discuss with you if you have any problems with the topics, just in case you didn't get enough material or anything like that on the topics. And starting on Tuesday, what I'm going to do is be available for you if you want to have any questions, or if you want to have any parts repeated from the course. Okay, so depending on what you see on Sunday about the contents of the final exam, you should feel free to send me the topics that you want me to explain further on Tuesday or on other day. Okay, next week we're going to have only Sunday and Tuesday. We're not going to have Thursday. We don't need Thursday anymore. We usually had 2 lectures per week. We increased that to 3 lectures because actually we weren't sure we are able to cover the whole material during the reduced duration of the term. But I think we are now fine. So basically, we're going to have a review lecture on Tuesday, and the next week, basically the following week, we'll have also on Sunday and Tuesday, we're going to have review lectures. I would be more than happy to repeat any of the lectures that we had before. If you feel that a particular topic of the course wasn't covered properly, I would be happy to repeat it again. If you have any particular questions about particular problems or anything like that, I would be happy to also help you with them. Okay? Do you have any questions or concerns about the course? Any questions?
No, thanks.
So for now, we agree that we have a lab exam on April 7th, inshallah. Okay?
Inshallah.
Okay. So I hope all of you come or attend on Sunday so that we can agree together on the topics that will be included in the exam. I'm going to post them on Blackboard, but actually I'm going to go over them with you on Sunday so that you understand exactly what I mean by each one of the topics. Okay?
Okay.
I don't want you to have any confusion about this part. Please don't worry about the final exam. It's going to be straightforward. It's not going to have any tricks or anything like that. You probably saw already the multiple choice. It's exactly going to be the same format as a midterm, but actually maybe maybe an additional 2 problems, 3 problems, something like that, just to cover the additional parts that we had. But that's it. Okay, it's not going to be that big of a deal, basically. Okay, just make sure that we have evaluated every part, and basically it's going to be just straightforward. If you know exactly how to solve the homework problems, you'll be fine. Okay?
Okay, so. Okay.
Okay. So inshallah, if you have any questions, please send them to me. If you have any concerns after I send the list of topics, please plan to talk to me about them on Sunday, inshallah. Okay?
Okay.
And please submit your homeworks. If you haven't submitted your homework, please submit by the deadline I set last time. Okay?
Okay. Good.
Okay, good luck, inshallah. Stay safe, please. Okay?
Okay, inshallah. Thank you.
Inshallah.
Shukran.
Thank you, Doctor.
Shukran.
Thank you,
Salam alaikum.
Doctor.
Salam alaikum.
Salam alaikum.